Hey everyone. Today we continue our focus on orbits and astronomy. Specifically, we will learn about Kepler's laws, which are to the heavens and celestial mechanics what Newton's laws are to more down-to-earth mechanics. To begin, let's go with a brief history lesson. In the late 1500s, there was a Danish astronomer named Tycho Brahe who began to make the first real detailed measurements of the locations of the stars in the sky. He was so accurate that he got to within 1 arc-minute of accuracy. To give you an idea, the moon's width is approximately 30 arc-minutes, and so he was able to pinpoint the locations of stars to within 1/30th of the width of the moon. Not a bad feat considering it was the 1500s, and he didn't really have a good working telescope. Now, he couldn't make a whole lot of sense of all the data because there were just a lot of numbers, and so he hired a mathematician named Johannes Kepler to look over the data. Kepler was able to find not only useful patterns, but actually 3 major laws which to this day we continue to use in modern astronomy. It's those 3 laws that we discussed today. The first of the laws that Kepler discovered was that planets move in elliptical orbits. Now, it was believed that planets moved in circular orbits, but Kepler noticed that the planets are not perfectly circles. In fact, a planet's orbit can vary tremendously, and the eccentricity of the orbit is something that we can measure. Eccentricity is how elliptical an orbit is, and for a perfect circle, we say that it has an eccentricity of 0. The most extreme, flattest ellipse that we could think of would have an eccentricity of 1, and all planets have an orbit somewhere in between those 2 values. Not only planets, but asteroids or anything that moves around the sun for that matter travels in this elliptical orbit with the sun at one of the focuses. Kepler's second law is best summarized by the picture shown below. He noticed that if you plot the location of a planet at equally spaced intervals of time, and drew lines from those locations to the sun, the shapes that are formed all have the same area. As a specific example, if you look at this area from A to B and back to the sun, that relatively big looking area is actually equivalent to this sliver shown from I, H, and the sun. Now, the only way that that can happen is if in some parts of the orbit the planets move faster than in other parts of the orbit. Kepler didn't know it at the time, but actually this is an excellent proof of the angular momentum conservation law, which was discovered much later. Kepler's third law is probably the most useful of the rules because it provides a formula that relates the period of an orbiting body with the radius of its orbit in a proportion. Specifically, it says that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. The semi-major axis is required because some of these orbits are ellipses and not true circles, and so the semi-major axis is the biggest radius, if you will, of the ellipse. This can be summarized in the proportion r cubed over t squared for one object is equal to r cubed over t squared for some other object. I like to remember this with the mnemonic Rubik's Cube over time squared. Kind of cheesy, but it helps me remember which one is cubed and which one is squared. Now, this ratio is constant for all of the objects that orbit a common mass. So for each of the planets that surround our sun, or all the satellites and our own moon that surround Earth, or for all the moons that go around a planet, for instance, all 63 of them that go around Jupiter. Now, we can verify this quickly by looking at the planetary data sheet that you guys have in the back of your notes. Here's that same chart, only in an Excel file. First of all, I would like to just look at the 2 quantities of interest, the orbital period and the radius. So, I will pull just the orbital period and the distance from the sun, which is its radius. Now, each of these things, except for the moon, are all things that orbit the sun. So let me just hide the moon's data temporarily. And if we calculate the ratio of the distance cubed, that will be this square raised to the third power, and divide it by the period squared. For Mercury, this gives us a value of about 25. And if I drag the same formula over to each of the other planets, notice how each of the planets, that same value shows up as about 25. If you used any other type of proportion, for instance, just the simple distance divided by period, notice that these values vary significantly from planet to planet. Some are 0.6 and 0.4, and others go as low as Pluto here is 0.06. Those are not equal. The only way that they're equal is if you use that strange proportion where the radius is cubed and the period is squared. So, let's use this in a calculation. If we observe that the planet Saturn seems to take 29.4 years to complete an orbit around the Sun, which we can see by comparing its location against the background stars, how far away from the Sun is Saturn on average? To answer this question, what we'll do is we'll set up a proportion that compares the knowledge of the information we know about Earth to that of Saturn. The proportion we'll set up is that the orbital radius cubed of Earth over the period squared of Earth is going to equal the orbital radius of Saturn cubed over the period of Saturn squared. Now, the orbital radius of Earth, we could look up that actual number, but a convenient number to use in this particular problem is to say that the Earth is 1 astronomical unit away from the Sun. That's what an astronomical unit is. It's the distance between the Earth and the Sun. It's not a made-up unit. It really is a unit that we use quite often. So we'll say that 1 AU is the radius of the Earth, and that's cubed. And the period of the Earth is 1 year, so I'll call that 1 year squared. When you're using this particular proportion, it does not matter what units you use as long as you're consistent. If I used astronomical units for this proportion, then my answer will come out in astronomical units for the distance that Saturn is away. And I'll have to use years as our period, which is convenient because that's what was given to us. So, on this side, Saturn's time period is 29.4 years, and that's squared. And so our answer will be in astronomical units. And we can solve this proportion by cross-multiplying. On the one side, we've got 1 times r cubed, or simply r cubed for Saturn, is equal to 1 cubed, which is 1 times 1 times 1 is 1, equals 29.4 squared. And so the radius of Saturn's orbit is equal to the cubed root of 29.4, or 29.4 raised to the 2/3 power. You can calculate this a couple of ways. The way I would do it is to type 29.4 and then raised to the 2/3 power, and you'd have to put 2/3 in parentheses. That gives us a value of 9.5 astronomical units, or essentially 9.5 times further away from the Sun than the Earth. Another way is to go into the math menu and find the cubed root of 29.4 squared. And notice we get the same value. Now, if we wanted to know exactly how far away Saturn is from the Sun, then we'd have to convert astronomical units into kilometers or miles by looking up the distance away from the Sun that the Earth is. The last question I have brings together the concepts from orbits, centripetal force, and these rules from Kepler's law in one final question. What is the mass of a planet that has a moon that orbits it at a radius of r with a time period of t? I think it's kind of remarkable that we can even ask this question, that we can calculate what the mass of a planet is simply by observing the fact that A, it has a moon, and that that moon orbits at a specific location and with a specific time period. To make progress in this, we're going to use the same starting point that we used in the orbits video, and that is that the centripetal force required is provided entirely by the gravitational force. So, if we start to substitute some formulas, the centripetal force formula is mv squared over r, and here I use a lowercase m to indicate that this is the mass of the moon as it's going around, the thing that is moving around in a circle. And then the gravitational formula is capital G, and it's the mass of the moon times the mass of the planet divided by the distance between them squared. And that would be the radius, the orbital radius as well. Our goal in this problem is to figure out what this mass is equal to. And so to do that, perhaps I will multiply both sides by r squared and divide both sides by m, little m that is, and capital G. And so over here, multiplying by r squared and dividing by little m and capital G, we see that the m's cancel out. And so the fact that we don't know the mass of the moon is irrelevant. We see that r squared over r reduces to having an r on top. We've got v squared, which is the speed that the moon is orbiting at. And then on the bottom, we've got the gravitational constant g. On this side, the lowercase m's canceled out, the gravitational constant canceled out, and the orbital radius squared canceled out, and so all that's left is a formula for mass. Now, to get the fact that we know what the period is, we need to use a substitution. We learned in the orbits chapter that the velocity of an orbiting object is equal to the circumference of its orbit, 2 pi r, divided by the time period. And so if we make a substitution and plug this in for v, then we've got r, 2 pi times r divided by the period, and that factor is squared, and all that is divided by g. That's the same thing as putting r and g, and then dropping this down, putting the t in the denominator, squared, and 2 squared, pi squared, and r squared. And if we clean this up a little bit, we can get 4 pi squared, and r times r times r is r cubed. And on the bottom, we've got g and t squared. And that is what mass is equal to. And so, as a whole, we have a formula that the mass of the object in the middle, that things are surrounding, is equal to Kepler's ratio, that's r cubed over t squared, times the coefficient of 4 pi squared over g. Thanks for watching, and be ready to use this formula in a lab in the next couple days, where we will take a look at some pictures of the moons that are going around Jupiter on various days. And from that information, we should be able to calculate what the mass of Jupiter is without ever leaving home.